In the final step, we'll be finding the second derivative of the function and use it to determine the concavity of the graph. Let's go. So what is the second derivative? Well, the second derivative is simply the derivative of the first derivative, right? So let's pull out the result from question D. Okay, so from question D, we found the first derivative to be 48x squared over the square root of x cubed plus 8. So from question D, we found the first derivative to be 48x squared over the square root of x cubed plus 8. Okay, so now let's take the derivative of this guy, and that's going to be our second derivative. So our second derivative is, well, since we are dealing with a quotient, we should apply the quotient rule to find the derivative, right? So the quotient rule, without thinking, first thing we gotta do is what? Square the bottom, right? So we're gonna square the denominator, right? And what's the denominator? The denominator is this guy right here, right? X cubed plus 8, the whole thing squared. Okay? Now up at top, we're simply gonna apply DOOD, right? D-O-O-D. So D, O means nothing, O and D, right? D-O-O-D, do, right? Like, come on, dude. Okay, let's go. So the numerator is 48x squared. Okay, so 48x squared, 48x squared. And then the denominator is this guy, right? Is x cubed plus 8, the whole thing squared. X cubed plus 8, the whole thing squared. Okay, good. So let's go. So this is, now for the bottom, square and square, that becomes what? To the power of 4, right? So we have x cubed plus a to the power of square square, that will give us to the power of 4. Now for the numerator, we have, look, okay, first, we're going to take the derivative of 48x squared, and that's going to give us 96x, right? And we'll leave this guy untouched. So that's just x cubed plus 8 squared, right? Simple. And minus, now we'll leave the 48x squared untouched. 48x squared. And now we're going to take the derivative of this guy right here. Okay, guys, in this case, we have to apply the chain rule, right? Because the thing inside the bracket, the term inside the bracket is no longer just a simple x, right? See, look, whenever we take the derivative of a function and inside the bracket is not a simple x, then we have to remember to apply the chain rule, right? So in this case, the chain rule, the derivative of bracket squared is what? Well, first, here we have a power function, right? Because we have something to the power of 2, the power function. So let's apply the power rule to find the derivative first. So applying the power rule, we bring the exponent to the front, 2, and the exponent minus 1. So 2 minus 1, we get 1. Guys, don't forget about the chain rule, followed by the chain rule part, the derivative of whatever inside the bracket. Okay? So in this case, the thing inside the bracket is x cubed plus 8. So x cubed plus 8, x cubed plus 8, x cubed plus 8. So at the end, the derivative is, we have then the derivative is, we have 2 times x cubed plus 8 to a power of 1, and we don't have to write it, right? And then times, now we have to take the derivative of this polynomial. So the derivative of x cubed is 3x squared, right? And derivative of any constant is 0. Okay? Yeah. So the derivative of this guy here x cubed plus a, the whole thing squared, is right here. Okay, so I'm just going to copy this down. So we have times 2 and then x cubed plus 8 and then 3x squared. Okay? Yeah! Cool. Now, yeah, so let's do more cleanup. In the denominator, we have x cubed plus a to the power 4. Now for the numerator, guys, before we make an attempt to expand everything, which might get pretty ugly, let's see if there's any common factor we can take out first, okay? Now, look, guys. Guys, first of all, look. Look at this guy right here. We have 48x squared and then times 2, right? Times 2. And that's going to give us what? 96x squared, right? And guys, that's nice because 96, see, something in common, right? So we can take it out. Okay, so I'm gonna just replace this with 96x squared, okay? So I'm gonna replace this part with 96x squared. Okay? Yeah. Now, okay, so let's see. So, let's see, so we have 96, we can factor it out. Any more common factor? Yes, we have x right here. We have another x right here, so we can take it out. So take out the x. Anything more? Yes, right here. X cubed plus 8. X cubed plus 8. So we can take it out. X cubed plus 8. Okay? Now, what do we have left? So after taking out a common factor, what do we have left? Then we have, let's see. So let's look at the first term, right? Let's look at the first term at the numerator. So we already took out 96, so that's gone. And we took out x, so that's also gone. And we took out 1 x cubed plus a. So here we have 2, right? Because we have squared. So if we take out 1 x cubed plus a, we still have 1 left, right? So for the first term here, we still have 1 factor of x cubed plus 8 left. Okay? Now minus. Now for the second term here, let's see what we have left after we take out the common factor. So we took out 96, right? We took out 96, we took out 96. We took out 1x, right? We took out 1x. So here we have x squared, we have 2 x's, right? So we take out 1, we still have 1 left. We still have 1 left. Okay? Now we also take out x cubed plus a. We took out x cubed plus a, so that's gone. And that's it. And we still have 3x squared, right? So we still have 3x squared. Okay, so at the end, I'm running out of space again, so I'm going to do it right here. So at the end, what do we have? So we have, bottom we have x cubed plus a to the power 4. And up top, we have 96x times x cubed plus a times, let's see. So what do we have in the middle? So we have x cubed plus a, we have x cubed plus a, and minus x times 3x squared, that's going to give us 3x cubed, right? That's going to give us 3x cubed. So we're going to have minus what? 3x cubed, right? Right here, 3x cubed. 3x cubed. Okay? Yeah. So, let's do more cleanup. And we have x cubed plus a to the power of 4. And up top we have 96x times, whoa, guys. This is beautiful here. I see another common factor between the numerator and denominator. Look, x cubed plus a, x cubed plus a. But on the bottom we have 4 of them, right? So after cancel out, we still have how many left? 3 at the bottom, right? So we just have 3 at the bottom left. Oh, beautiful. Oops. Okay, beautiful. Okay, cool. Now, so now at the numerator we have 96x, and well, this is pretty clean. Times, no, let's clean up the thing inside the bracket. We have x cubed minus 3x cubed. Then we have negative 2x cubed, right? And then plus 8, and then plus 8. Okay, and we're done. Whew. So it's pretty, quite a hairy process, right? Pretty long. Okay, but at the end we get a pretty beautiful result, would you say? Yeah. Okay, so the second derivative is, let me just write down the result. So the second derivative is equal to, on the bottom we have the cubic of x cubed plus 8. X cubed plus 8. Now the numerator we have 96x times negative 2x cubed plus 8. Okay, that's it. So with the second derivative in place, we are now ready to find the possible inflection points by equating the second derivative to 0. So let's do that. So to find the possible inflection points, we simply make the second derivative equal to 0, right? And in this case, our second derivative is right here. So 96x times negative 2x cubed plus 8 over x cubed plus 8 cubed must be equal to 0, right? Yeah. So let's solve for the equation right here. I'm gonna first try to get rid of the denominator by multiplying both of the equation by the denominator, right? So I'm gonna times x cubed plus a cubed. On this side of the equation, same thing, times x cubed plus 8 cubed, right? And by doing that, we're able to cancel out the denominator on this side of the equation, right? Okay, so at the end, we are left with a more simplified equation. So cancel out the denominator, we now have 96x times negative 2x cubed plus 8 is equal to 0 times anything is 0. Okay, now let's look at the equation we have here. What does that tell us? Well, if the first guy times the second guy is equal to 0, that tells us that either the first guy is equal to 0 or the second guy is equal to 0, right? Yeah. So let's solve the equation in each case. So in the first case, if 96x is equal to 0, that basically tells us that x then must be 0, right? Because 0 times 96 is 0, right? And let's solve for x in the second case right here. So to solve for x, we get, you know what, first I'm gonna move negative 2x cubed to the other side. And that way it becomes positive, right? So Negative 2x cubed, move to the other side, becomes positive 2x cubed, is then equal to 8. Right? Okay, and then divide both sides of the equation by 2, we get x cubed is then equal to 4. Right? And then, so to solve for x, we simply add cubic root to both sides of the equation, right? Then we get x then is equal to the cubic root of 4. Okay? And just like that, we found the possible inflection points at x equals 0 and cubic root of 4. Cubic root of 4. Next, let's put the possible inflection points on the number line to divide the number line into intervals. Then we're going to use the concavity test to determine the concavity of the graph on each interval. So let's go. So we have possible inflection points at x equals 0 and at x equals cubic root of 4. Cubic root of 4. Okay? Now, let's also put down the vertical asymptote on the number line. So remember, we have a vertical asymptote at x equals negative 2. So let's also put down negative 2 on the number line. Why? Why? Because, look, vertical asymptote divides up a graph, right? So we do want to know the concavity of the graph on the left side of the vertical asymptote, and we also want to know the concavity of the graph on the right side of the vertical asymptote, right? So that's why it's also a good idea to put down the vertical asymptote on the number line. So then we can use the concavity test to help us determine the concavity of the graph on each side of the vertical asymptote. Okay, so let me just make a note. So this guy is not possible inflection points, unlike these two, okay? This guy is a vertical asymptote. Vertical asymptote. Okay? Unlike the other two, they are the possible inflection points, right? See, this is possible inflection point, right? Same as this guy. This is also another possible inflection point, right? Okay, so we are now ready to perform the concavity test to determine the concavity of the graph on each interval. Okay, so let's go. So start with the first interval right here. Okay, so what we do is we just pick any number within this interval and plug it into the second derivative expression to see if we come up with positive value or negative value. And if the second derivative is positive, look, if the second derivative is positive, what does that tell us? The curve, the graph of the function is concave upwards, right? Concave upwards. Now, if the second derivative is negative, that tells us the graph of the function is concave downward, right? So let's find out. Let's find out. Okay, so guys, give me a number on the left side of negative 2. How about, let's try negative 3. Let's try negative 3. Okay, so let's plug in negative 3 into the second derivative expression. Okay, yeah. So let's see. Okay, so guys, look. We don't have to find out the exact value. Okay, we just have to find out if the final outcome is positive or negative. Okay, so let's plug in negative 3 into x in the second derivative expression. So negative 3 times 96 is going to give us a negative value, right? Now, negative 3 cubed, which is negative 27, times negative 2, see guys, look, negative 3, there's a cube right here, right? There's a cube right here. So negative 3 cubed is negative 27 times negative 2. That's going to give us positive 54. Plus a, that's going to give us a positive value, right? So at the numerator, we have a positive value times a negative value, and that's going to give us a negative value at the end for the numerator, right? How about at the denominator? Let's plug in negative 3 right here. So negative 3 cubed is negative 27 plus 8, and then we get a negative value, right? Negative 27 plus 8, we get a negative value, and negative value cubed, still negative, right? So at the end, at the denominator, we have a negative value. So now let's look at the overall value. So we have a negative at the numerator, a negative at the denominator. So a negative number divided by another negative number, that's going to give us a positive value at the end, right? So plugging negative 3 into the second derivative, guess what? It's going to give us a positive outcome at the end. So it's going to give us a positive outcome at the end. And that tells us what? On the left side of negative 2, the graph is concave up, right? The graph, see positive. The graph is concave upward, right? Yeah. Okay? Yeah. So concave upward. Concave upward. I'm just gonna say concave up. Okay? Cool, cool, very cool. Next, let's test the second interval right here. So let's test the interval between negative 2 and 0. So guys, give me a number between negative 2 and 0. How about negative 1, right? So let's test negative 1. So let's plug in negative 1 into the second derivative expression. Okay, so what do we have? So negative 1 times 96, that's going to give us a negative value. Okay, and now right here, we have negative 1 cubed, that's still negative 1, times negative 2, that's going to give us 2, right? And then 2 plus a is equal to 10. Okay, okay, cool. So now the second bracket here at the numerator is positive. Okay, so at the end, up at the numerator, we have negative times positive. That's going to give us a negative value, right? Okay, cool. How about the denominator? Plug in negative 1 right here. Negative 1 cubed is negative 1 plus a is still plus a, we get a 7, right? See, negative 1 cubed is negative 1 plus a, we get 7. And 7 cubed is a positive value. So at the end, we have negative at the numerator, positive at the denominator. And a negative number divided by a positive number, that's going to give us a negative outcome, right? So by plugging negative 1 into the second derivative expression, we get a negative outcome at the end. A negative outcome at the end. And what does that tell us? That tells us that the graph of the function is concave downward between negative 2 and 0. Concave down. Right? Mm-hmm. Simple, right? Very cool. So let's go. Let's test the third interval right here. So let's test the interval between 0 and cube root of 4. Well, first of all, cube root of 4 is roughly what? Well, let's think about this, right? Cube root of 1 is 1. Cube root of 8 is 2, right? Then cube root of 4 must be a value between 1 and 2. Let's just say it's 1 point something. Okay, so this is 1 point something. So this is equal to 1 point something. Okay, so guys, give me a value between 0 and 1 point something. How about 1? Right? So let's use 1 as a test value for this interval. Okay? So plugging 1 into the second derivative expression, 1. Okay, we're going to plug in 1, 1, 1. So 1 times 96 gives us a positive value. So 1 cubed is 1 times negative 2, that's negative 2, plus a, that's positive 6. So still positive. So at the numerator, we have positive times positive, and that's just going to give us positive at the numerator. Now at the denominator, 1 cubed is 1, 1 plus a is 9, and 9 cubed is also positive at the denominator. So at the end, we have positive divided by positive, and that's going to give us a positive outcome, right? Positive outcome. Cool. So, as it turns out, between 0 and cube root of 4, the graph is concave positive, concave upward, right? Concave upward. Beautiful. Next. let's test the very last interval, okay? So we're almost done. Cool. Okay, so guys, let's test the very last interval. So the interval for x value greater than, on the right side of cube root of 4, greater than cube root of 4. So give me a value that's greater than 1 point something. How about 2, right? So let's use 2 as our test value. Oops. Let's use 2 as our test value, okay? So plug in 2 into the second derivative expression. What do we get? So 2 times 96, that's going to give us positive value. Now here, 2 cubed is 8. 8 times negative 2 gives us negative 16. And plus a, that's going to give us a negative value, right? That's going to give us a negative value. So at the end, up at the numerator, we have positive times negative. That's going to give us a negative value at the numerator. Now at the denominator, we have 2 cubed is 8. 8 plus 8, 16. 16 cubed is positive at the denominator. So at the end, we have a negative number divided by a positive number. And that's going to give us a negative outcome, right? That's going to give us a negative outcome. Okay, very simple, right? So if the second derivative is negative, that tells us that the graph is concave downward, right? So for on the right side of cube root of 4, the graph is concave down. Now, knowing the intervals of concavity, which is right here, let's use the concavity information to help us sketch an even better graph. One that's better than a graphing calculator. Let's go. First of all, let's talk about concavity. How is a graph supposed to look like when it's concave up? Well, let me show you a memory aid. When your spirit is high up, you smile, right? You smile like this. A big smile, right? And that is a graph concave up, okay? Yeah. Now, on the contrary, when you are feeling down, you frown, right? You frown like this. Right? Really sad, right? Well, and that is a graph concave down. Okay? Yeah, so for our graph here, the part of the graph that's concave up, I'll sketch it with red. The part of the graph that's concave down, I'll sketch it with blue. Okay, so let's go. So back to the intervals of concavity right here. Okay, so let's go. Let's look at our first interval here. On the left side of negative 2, we know the graph what? The graph is concave up. The graph is concave up. So on the left side of negative 2, the graph is concave up. See, and that's why we see, look, the graph is concave up. So our prediction earlier was actually correct. Right? The graph is concave up. Can you see that? Concave up. Right, look. Okay, can you see this is part of concave up? Right, see, look, concave up. See, concave up, this is basically the right half of concave up. Right, see, look, concave up. You see that? Yeah. Good? Yeah. So good, very good. Next. Now, for the second interval here, between negative 2 and 0, the graph is concave down. The graph is concave down. So between negative 2 and 0, the graph is concave down. So and once again, concave down, right? So look, it's this part. Concave down. Can you see that? Concave down. And this is the left half of concave down. Can you see that? Look, this right here is actually this part. the left half of concave down, right? Concave down. You see that? Right here. Concave down. Concave down. Okay, good. And next. Between 0 and cubic root of 4, the graph is concave up. So between 0 and cubic root of 4 is a number that's slightly bigger than 1, right? So cubic root of 4 is roughly right here. So this cubic root of 4 is roughly right here. Okay, that's cubic root of 4, roughly right here. Okay, now, so between 0 and cubic root of 4, the graph is concave up. So look, from here, 0 to cubic root of 4, which is roughly right here. Okay, from 0 to cubic root of 4, the graph is concave up. See, concave up. Concave up. Right, concave up, which is what? Which is actually this part of concave up, right? Can you see that? Concave up. Concave up. Okay? Cool. Next. For the last interval, on the right side of cubic root of 4, the graph is concave down. So on the right side of cubic root of 4, the graph is concave down. Concave down. So concave down. You see that? Beautiful, right? Yeah, and then once again, this concave down is, look, this part is here, right? The left half of a concave down graph, right? Look like this, right? Like this, okay? Yeah, you get the idea now? It's pretty cool stuff, right? Now, we are ready to identify the inflection point on our graph. Guys, remember, what's an inflection point? Well, an inflection point is defined as what? Inflection point occurred where the direction of concavity changes, right? So anytime we have change of concavity, we have inflection point, right? So check this out, guys. So guys, I'm gonna note down the inflection point with pink, okay? So pink, hot pink. So pink represents inflection point. Okay, now look. Now look, so here, see now look. On the left side of -2, graph concave up. On the right side of -2, the graph concave down. So there's a change of concavity at -2, right? However, -2 in this case cannot be considered as the inflection point because at -2, we don't have any point. Right? There's no point on the graph that's sitting at -2. In fact, at -2, we have vertical asymptote, right? Yeah, so -2, although there's a change of concavity, we don't have an inflection point at -2 because -2 is where we have the vertical asymptote. In fact, asymptote, what does asymptote mean? Asymptote means what? The graph of the function will get closer and closer to asymptote, right? But never touch, right? Yeah, okay, cool. Now, let's look at this then. Now check this out. At 0, guess what? The graph goes from concave down to concave up. You see that? Goes from concave down to concave up. So there's a change of concavity at 0, and therefore 0 is an inflection point. Yes. So 0 is an inflection point, which I'm gonna note it down with pink, okay? Yeah. Now let's keep going. Now, how about at x equals cubic root of 4? Do we have an inflection point? Yes, because look, at x equals cubic root of 4, the graph goes from concave up to concave down. Can you see that? Concave up and to concave down. So there's a change of concavity at cubic root of 4, right? And then therefore we have another inflection point at cubic root of 4. Okay? So yeah, so we have here and here we have inflection points. Inflection points. Okay, and we can also see that on the intervals of concavity, right? See guys, look. See, change of concavity, and then, well, we can see that on the intervals of concavity, because look, from concave up to concave down, see? Change sign. Whenever the second derivative changes sign, we should be looking for inflection points, right? See, positive, negative. Second derivative changes sign. Okay, so we have to look at -2. However, -2 happens to be the vertical asymptote, right? So not inflection point. Next. Does the second derivative change sign here? Yes, it goes from negative to positive. So second derivative changes sign, guess what? We have an inflection point at x equals 0, right? Now how about this? At x equals cubic root of 4, does the second derivative change sign? Yes. See, second derivative change goes from positive to negative. So therefore, whenever there's a change of sign in second derivative, or we can say whenever there's a change of concavity, we have inflection point, right? We have inflection point right here as well. Cubic root of 4. Okay? Yeah. Okay? So just like that, we verify the inflection points. Okay? So that's how we verify inflection points. Because remember, in the earlier step, we identified, we found the possible inflection point by what? By making the second derivative equation equal to 0, right? Yeah, so that's what. And then by making the second derivative equation equal to 0, we found x to be 0 and cubic root of 4. And we say they are the possible. We say they are the possible inflection points, right? But now, once we have the intervals of concavity, we can verify. We can verify, right? See? And as it turns out, second derivative changes sign, guess what? Then we successfully verify that this is indeed a real inflection point. So it's not possible anymore. It is true. It is indeed an inflection point at x equals 0, right? And second derivative changes sign, and guess what? This guy is indeed an inflection point. So it's not possible anymore. It is truly an inflection point, right? Okay? Yeah. So now, so we have two inflection points. So we have inflection points. We have two of them, right? At x equals 0. So we have inflection point at x equals 0 and at x equal cubic root of 4, right? Now, to describe a point, we need to provide the x coordinate as well as the y coordinate, right? So now we know our first inflection point is at x equals 0. Now, what's the y coordinate for this point? For the point, right? What's the y coordinate for this point? Well, to find y is easy, right? So we basically just plug in x value into the original function, right? So because f of x is the same thing as y, right? F of x is the same thing as y, okay? So to find the y coordinate for this inflection point, we simply plug x equals 0 into the function. So let's plug x equals 0 into the function. Then we get 0 cubed is 0 minus a, we get negative a at the numerator. Now at the denominator, 0 cubed is 0 plus a. We get 8 at the denominator. Okay, and negative 8 divided by a, we get negative 1. So when x is equal 0, y is equal to negative 1. And that is going to be our y coordinate for the first inflection point, right? Which is actually the y-intercept we found earlier, right? So this point, this inflection point has a coordinate 0 and negative 1, which happens to also be our y-intercept, right? Now how about the second inflection point here? Well, we know the x-coordinate is cubic root of 4, right? It's cubic root of 4. Now what's the y-coordinate? Well, easy, right? So when x is cubic root of 4, how do we find the y? How do we find the corresponding y-coordinate? Same thing, plug into the original function. Guys, remember, when we want to find the y value, because y is the same thing as f of x, okay? So whenever when we try to find the y value, remember, you have to find the y value from the original equation. Okay, because a lot of students, they get too excited when they accidentally plug in the x value into the second derivative expression. That wouldn't make sense, right? Because y is the same thing as f of x, not f double prime of x, okay? Not the second derivative of the function, okay? Cool. So to find the corresponding y coordinate, remember, we use the original function because f of x is the same thing as y. Okay? Yeah. So we have x cubed minus a at the numerator. On the denominator, we have x cubed plus a. Okay, now for the x value for this inflection point, we're gonna plug in x as cubic root of 4. So x is cubic root of 4. X is cubic root of 4. Okay, so now up at the numerator, guys, look. The cube and cubic root cancels out, right? Cancels out. Then we just have 4. 4 minus 8 is negative 4, right? And same thing, right? For the denominator, cube and cubic root cancels out. Then we just get 4 plus 8, then we get 12. Okay, so at the end, negative 4 over 12 can be simplified as negative 1 over 3, right? Because divided by 4, we get 1. Divided by 4, we get 3. Okay, so when x is cubic root of 4, the corresponding y coordinate is negative 1 over 3. Okay, so on our graph here, our second inflection point right here has x coordinate, cubic root of 4, has y coordinate, negative 1 over 3. And then we are completely done. See, as you can see, we successfully sketch a graph that's very, very precise, and that actually provides more information than the graphing calculator, right? Because look, guys, if you were to plot this function on a graphing calculator, yeah, you get a curve that looks, something like this. But guess what? Does the graphing calculator tell you where the inflection point is? No. Right? But hey, on the graph that we built on our own, hey guys, look, we are able to identify exactly where the inflection points are on the graph. Right? So this is really cool stuff.